LongTraceRL, learning long context reasoning from search agent trajectories with Rubric rewards. That is the paper today, and the core insight here is that current large language models fundamentally fail at long context reasoning.
Right. They fail miserably because current reinforcement learning methods, they use these really weak, like randomly sampled distractors, and the rewards are totally sparse, just outcome-only checks.
Exactly. And this paper completely rewrites that playbook by using a real search agent's actual mistakes to generate brutally hard tiered distractors.
Yeah, and then they apply this fine-grained rubric reward, so it checks the model's reasoning at every single entity hop.
But, and this is the crazy part, it only applies that reward if the final answer is actually correct. And the result is a massive performance jump, up to 5.7 points on a 4B model across 5 major long context benchmarks.
Which is huge for a model of that size.
It really is. So if you're an AI researcher or, an ML engineer building RX pipelines or training long context models, you really need to pay attention to this.
Absolutely. The positive-only rubric and that trajectory tiered data assembly, they're basically practical recipes you can use right now to stop your models from hallucinating.
Or taking those cheap reasoning shortcuts. But before we get into the results, we really need to understand the bottleneck this architecture is actually fixing.
Right, so we have to look closely at RLVR, which is reinforcement learning with verifiable rewards. Historically, these methods have leaned almost entirely on outcome-only rewards. So a model generates a chain of thought, spits out an answer, and a programmatic judge just looks at that final string.
And it assigns a binary score, right?
Yeah.
Like a 1 for correct, 0 for incorrect.
Exactly. Which, works reasonably well for self-contained short context tasks. Things like basic math word problems.
Or simple coding functions, where the reasoning path is really tight.
Yeah, but applying that binary outcome to a context window of, say, 100,000 tokens or more, it creates an incredibly sparse signal.
Because there's just a massive gulf between digesting 100,000 tokens of raw text and outputting that final target word. I mean, the model is making thousands of micro decisions along the way.
Which leads to this phenomenon we call coincidental success.
Oh, this is fascinating. Explain that.
So a model navigating a massive document can easily guess the right answer for completely flawed reasons. It might hallucinate a connection between two unrelated paragraphs.
Cite the wrong entity entirely.
Right. But it still manages to output the correct final string by pure chance. And that coincidental success satisfies the binary outcome reward.
So the model gets a 1.
Yep, it gets a 1. But it masks all those intermediate retrieval and reasoning failures. The model learns absolutely nothing about how to actually navigate a massive document.
But it gets reinforced for its flawed process anyway. It's basically getting a dopamine hit for being lucky, not for being smart.
Exactly.
It's like creating a complex calculus exam based only on the final number circled at the very bottom of the last page.
That's a perfect way to put it.
Right. Like, the student could have faked all the math, made 3 different catastrophic errors that coincidentally canceled each other out, and still gotten an A.
Yeah, and to make matters worse, the training data sets these models were using were heavily flawed to begin with.
Oh, yeah. The multiple choice distractors in previous training sets, they were basically from a history test when the question was about chemistry.
Pretty much. Prior methods built their training data using really short reasoning hops, maybe 2 to 4 hops at most.
Okay.
And when researchers wanted to train models for long context, they would take those short reasoning chains and just stuff the rest of the context window with randomly sampled, totally unrelated documents.
Just to hit the token count.
Right. So if the target query is about, say, the lineage of a specific 16th century monarch.
The distractor documents might be blog posts about modern meteorology.
Or recipes for banana bread, yeah. The model doesn't have to engage in any cognitive friction at all. It just runs a superficial keyword filter.
Because there's zero semantic overlap. Those distractors offer no real confusability. So the model never actually learns to read, it just learns to skim for the only document that mentions a castle.
Exactly.
Well, if random distractors are fundamentally too easy, how do the authors of LongTraceRL systematically generate distractors that actually force the model to reason?
That brings us to their data construction pipeline. They approach this by breaking the pipeline into 4 distinct steps.
Okay, lay it out for us.
First, they need to generate baseline questions. They use the KILT Wikipedia snapshot that stands for Knowledge-Intensive Language Tasks.
Right, which is essentially a really dense, highly verified knowledge graph built on top of Wikipedia.
Correct. And from there, they perform controlled random walks across the knowledge graph.
But they aren't just doing the standard 2 or 3 hops, right? They are forcing extreme 8-hop reasoning questions.
Yeah, 8 hops. It's a massive chain of dependencies. 8 sequential steps following hyperlinks from entity to entity. And to ensure these paths don't just, circle back on themselves or stay within a narrow domain, they insert what they call mad walks.
Mad walks?
Yeah, they're intentional random jumps to completely different regions of the knowledge graph.
That is brutal. So once they have this complex 8-hop path, what do?
They use a powerful instructor LLM to synthesize a natural language question. Crucially, the prompt strictly requires the LLM to paraphrase all the identifying names and dates.
So that ensures simple keyword matching just won't work. The model really has to understand the semantic relationships.
Exactly.
Okay, I have a question about this next part, though. You have this brutal 8-hop paraphrased question, but you still need the haystack to hide the needles in. This is where they deploy a real search agent. But my understanding is they only keep the data from the times the agent actually succeeds at finding the answer.
That's right.
Why throw away the failures? Wouldn't a failed search run provide the perfect examples of where an AI gets confused?
Yeah, it seems counterintuitive at first, but if an agent fails completely, its trajectory is often just random exploration or compounding hallucinations.
Oh, it just completely loses the scent.
Exactly. By filtering exclusively for successful runs, the authors ensure the recorded trajectory reflects real, meaningful, goal-directed search behavior.
I see. So the agent was actively, logically trying to solve the 8-hop problem.
Yes. And along the way to the correct answer, it stumbled on specific documents that looked incredibly promising but were ultimately dead ends.
It's tracking the shiny objects that actually tricked a competent system, not just the random garbage a failing system clicked on in a panic.
Precisely. And they extract those specific shiny objects to build their trajectory-tiered distractors.
Okay, what did that look like?
They divide them into 2 levels. Tier 1 distractors are documents the agent actively opened and read during its search, but ultimately chose not to cite.
Wait, so Tier 1 is literally just the stuff the agent opened?
Yeah.
Why is that a better distractor than, say, using a dense embedding model to find a document that shares 90% of the same vocabulary as the target answer? We've been using hard negative mining with embeddings for years.
It's a good question. Dense embeddings are limited because they only look for vector similarity in the latent space. They're just searching for semantic closeness or surface-level keyword matches.
Right.
A document might have the same vocabulary, but structurally, it doesn't represent a logical step in a reasoning chain.
Oh.
The trajectory-tiered distractors are behavioral hard negatives. They represent documents that an active reasoning agent actually evaluated as a highly plausible next step based on context.
So it's the difference between a document that just happens to use the word bank a lot versus a document about a riverbank that perfectly aligns with the geographical reasoning chain the agent was following.
Right, before it realized it needed a financial bank. That is the exact distinction.
Wow. And what about Tier 2?
Tier 2 distractors have lower confusability. These are documents that appeared in the search agent's query results, but the agent's internal logic determined they weren't even worth opening.
So they're superficially related, but unlikely to mislead a careful reader.
Exactly.
Which brings us to the actual assembly of the context window. They're building windows up to 128,000 tokens, but they don't just dump all this text into the prompt arbitrarily, do they?
Not at all. The assembly prioritizes stuffing the context with those highly adversarial Tier 1 documents first. They pack as many of those behavioral hard negatives in as possible.
If they haven't hit the target token link.
Then they fill the remaining space with Tier 2 documents and then shuffle the entire context block.
I want to look at the ablation data on this because the numbers are staggering. When you use standard or random distractors, how often do they actually overlap with the real reasoning path?
When researchers measure how often the distractor documents share the rubric entities, the essential gold entities needed to solve the problem, random distractors share those entities with the question only 1.35% of the time.
1.35%. So they're trivial for a model to ignore.
Very trivial. But the Trajectory distractors share entities roughly 50% of the time.
No way.
Yeah, and for the Tier 1 documents alone, that overlap reaches over 63%.
So the model is looking at a context window where over half the documents contain the exact entities it's looking for, but only one specific path of logic connects them correctly.
Yeah, exactly. It can't just skim for names. It has to read, comprehend, and actively discard highly plausible information.
Okay, now that the training data is this absolute minefield, how do the authors train the model to actually navigate it? Because sparse outcome rewards obviously won't cut it here.
This is where group relative policy optimization, or GRPO, comes into play, paired with their custom rubric reward.
Can you quickly frame GRPO for anyone used to standard PPO?
Sure, so proximal policy optimization usually requires a separate value model to estimate the baseline reward. That eats up massive amounts of memory.
Which you really don't want with a 128K context window.
Exactly. GRPO skips that by sampling a group of outputs for the same prompt and scoring them relative to each other. It's much more memory efficient.
So GRPO provides the relative scoring framework, but the actual signal comes from this rubric reward. How does the grading actually work?
Because the researchers built the data using that 8-hop kilt knowledge graph, they know the exact gold entities required for every single step of the reasoning chain.
Right.
They use these entities to provide fine-grained, step-by-step process supervision. The programmatic judge calculates a raw rubric score based on how many of these specific gold entities the model successfully recalls and uses.
But wait, if they just apply that score directly, I can guess exactly what happened.
That's hacking.
Yeah. The model is going to realize it gets points for mentioning specific nouns. So instead of trying to solve the complex 8-hop logic puzzle, it's just going to scrape the context window and word vomit every single entity it can find into the output to farm points.
Classic reward hacking,
Yeah.
which is why the authors introduce a brilliant catch, the positive-only strategy.
Oh, how does that work?
The rubric reward is only applied if the model gets the final outcome correct. If the final answer is wrong, the reward is multiplied by 0.
Multiplied by 0. Wow.
Yeah, it doesn't matter if the model cited 7 out of the 8 gold entities perfectly in its reasoning trace. If it fumbles the final answer, it gets absolutely nothing.
That completely neutralizes the reward hacking. It forces the model to actually use those entities to build a bridge to the solution. You can't just throw bricks on the ground and ask for points. You have to finish the bridge.
Exactly. The rubric reward essentially serves to differentiate among the correct responses within that GRPO group.
I see.
It gives higher relative scores to model outputs that arrived at the right answer through sound, verifiable intermediate reasoning, and lower scores to those that got the right answer by taking shortcuts or just getting lucky.
And there's a delicate balance here, right? Because the paper mentions a hyperparameter, alpha.
Yes. Alpha dictates the weight of this rubric reward versus the base outcome reward.
So what's the sweet spot?
The optimal alpha they found is 0.3. The rubric reward needs to act as a gentle guiding signal, not an overpowering mandate.
What happens if it's higher?
If you bump alpha up to 0.5 or higher, performance actually drops across the board. The rubric signal becomes too dominant, and the model starts getting distracted by finding NT-mentioned shortcuts again.
So it dilutes its focus on the main problem-solving objective. But at 0.3, process supervision perfectly complements outcome supervision.
Exactly.
Okay, so if the rubric reward stops the model from hacking entity mentions and forces real reasoning, how does that actually manifest when the model is reading a complex, conflicting document? Does it move the needle on the benchmark?
Oh, the scale of the testing proves it does. They evaluated this across multiple scales. Qwen 3.4b, a distilled DeepSeek R1.8b model, and Qwen 3.30b. LongTraceRL consistently beats highly specialized long context baselines like DocUA, LongRL, and LongRLVR.
Wow.
On the 4B model alone, LongTraceRL achieves a 5.7-point average gain over the base model and beats the strongest baseline by 2.5 points.
A 5.7-point jump on a 4B model is massive. To really understand what that looks like under the hood, we should examine the case studies from the AALCR benchmark. This is where you really see the cognitive friction.
Yeah, let's look at the first case study dealing with conflict resolution.
The prompt asks a question about a medium-sized Australian business with 450 employees. And it asks how many of these businesses would have coworker non-solicitation clauses.
But the prompt itself is laying a trap.
Right.
The prompt uses the phrase medium-sized, but deep in the source documents, the Australian Bureau of Statistics explicitly defines a medium business as having 20 to 199 employees.
So a business with 450 employees actually falls into the large business category.
Precisely. Furthermore, the source document provides 2 different statistical rates. One rate for businesses overall, which is 18.0%,
Okay.
and a specific rate for businesses with between 200 and 999 workers, which is 37.6%.
I can completely guess what the baselines do here. Older models trained without this rubric reward, they're just going to scan for the first percentage they see next to the word business, grab the 18%, do the math on 450, and output the wrong answer.
That is exactly what happens. The baseline takes the shortcut, calculates 560 times 0.18, and confidently outputs 101. It completely misses the definitional nuance.
But the LongTraceRL model handles it entirely differently, right?
Yeah, in its internal reasoning trace, it actively flags the inconsistency. It explicitly notes that 450 employees falls into the large category based on the text, and states that the term medium-sized in the user's prompt appears to be a misnomer.
Wait, it overrides the prompt's false premise.
Yes. It reclassifies the business based on the headcount evidence, selects the correct 37.6% rate, and does the math to arrive at 211.
That is incredible. It's actively correcting the user based on the context. So it can correct false premises with numbers, but what happens when the trap isn't numerical, but structural?
The second case study is great for that. It deals with pronoun ambiguity, which is notoriously difficult for LLMs over long contexts.
What's the prompt?
It reads, one company in the documents conducted a press release on July 27, 2023. There is only one customer with an explicit mention of which stock exchange it trades on. What stock exchange does this company trade on?
This company. That classic ambiguous pronoun hanging at the end of the sentence.
Yeah.
Does it refer to the issuer of the press release, or does it refer to the customer?
Exactly. The text establishes two clauses. The first refers to Digital Realty, which issued the press release and trades on the NYSE. The second clause introduces a customer found in a separate data table.
And the baseline models.
They merge the two clauses into a single entity. They assume this company refers back to the primary subject, Digital Realty, and they just output NYSE. They fail to pivot their attention to the customer.
Right, because tracing a pronoun back across 50,000 tokens of intervening text usually results in the model just defaulting to the most prominent named entity. So how does LongTraceRL parse it?
It breaks down the grammatical structure perfectly. First, it identifies Digital Realty as the issuer. Then, it actively scans Digital Realty's top 20 customer table.
Yeah.
It checks Oracle, IBM, Meta. It notes none of them have an explicit exchange listed. Then it finds Equinix, which the document explicitly lists as NASDAQ, EQIX. The model's trace shows it realizing this company refers to this specific customer, and it correctly outputs NASDAQ.
It ignores the superficial keyword gravity of the main entity and actually follows the grammatical logic. That covers explicit contradictions and ambiguous grammar. What about semantic rigidity?
The final case study looks at subtle qualifiers. The prompt to ask the model to retrieve documents that provide outlooks for the year 2022 within their scope. It's an inclusive criterion.
Meaning the document doesn't have to be exclusively about 2022, just has to cover that time period. I'm assuming the baseline model just hits Command-F for 2022 in the titles.
The baseline model secretly rewrites the question into a rigid keyword search. It scans the titles, finds a Deloitte document literally titled 2022 Engineering and Construction Industry Outlook, and stops.
Oh, no.
It completely discards another highly relevant document from the ACEC Research Institute.
Let me guess, because the ACEC document is titled something like 2021-2025 Engineering Industry Forecast.
Precisely. The baseline model is too rigid to map the year 2022 into a date range, but LongTraceRL iterates over every candidate document without taking that shortcut.
So it actually reads it.
It reads the ACEC forecast, recognizes that a 5-year forecast from 2021 to 2025 inherently encompasses the year 2022. It even pulls a specific 2022 projection from the body text to justify its decision, and correctly returns both documents.
Because it understands the inclusive scope. And it does all this because it was trained in an environment where simple keyword matching actively penalized it.
Exactly.
Bringing this all together for you guys building out there. The combination of behaviorally derived distractors, the trajectory tiered data, and a positive-only rubric reward, it fundamentally shifts the paradigm for long context RL.
It forces evidence-grounded reasoning step by step.
You cannot just give a model 100,000 tokens and a thumbs up at the end and expect it to learn how to critically read. You have to lay intelligent traps, and you have to grade the scratch pad.
By using the search agent's own behavioral failures to define what constitutes a hard distractor, you create a training curriculum that directly targets the model's actual architectural weaknesses.
Yeah.
It removes our human bias of what we assume a hard distractor looks like and replaces it with empirical agentic confusion.
Which leads me to a final, pretty provocative thought to leave everyone with.
Yeah.
If we are now using the behavioral failures of search agents to build the training curriculum for the next generation of models, does this imply a closed, autonomous, self-improving loop?
That's a fascinating idea.
Right, like, could future architectures automatically mine their own mid-generation agentic mistakes? Imagine a system that continuously generates its own optimal RL reward landscapes based on the exact reasoning traps it just stumbled into a millisecond ago?
It's totally possible. The
Wow.
training data wouldn't just be synthetic, it would be dynamically adversarial.
Evolving in real time alongside the model's intelligence. Something to chew on as you go back to your pipelines. You're watching AI Paper Slop. Thanks for joining us for this breakdown. Keep building.